In the first step, the acidic acid takes a proton, a hydrogen ion from the concentrated sulfuric acid. This creates a protonated carboxylic acid. Proton transfer from an acid catalyst to a carbonyl oxygen increases electrophilicity of carbonyl carbon. The proton becomes attached to one of the lone pairs on the oxygen, which is double bonded to the carbon. The transfer of the proton to the oxygen gives it a positive charge. There will be some degree of positive charge on both of the oxygen atoms and also on the carbon atom. The non-bonded electrons of the alcohol attack the positively charged carbonyl carbon to give a tetrahedral intermediate. Because the hydroxide ion is a poor leaving group, chemists increase the rate of esterification by adding catalytic quantities of acid to the acid protonates the leaving group, allowing the water molecule to leave. The presence of an acid catalyst increases the reactivity of the carbonyl group. The addition of the acid protonates the carbonyl oxygen, thus enhancing the carbon's reactivity to a nucleophile. In step 2, the positive charge on the carbon atom is attacked by one of the lone pairs on the oxygen of the ethanol molecule. The formation of the tetrahedral intermediate is encouraged because the carbonyl carbon of the acidic acid becomes more susceptible to nucleophilic attack. The carbonyl carbon is then attacked by the nucleophilic oxygen atom of the alcohol. In the third step, the intermediate compound loses a hydroxide ion, thus forming an ester with the carbonyl protonated. What happens in the next step is that the proton, a hydrogen ion, gets transferred from the bottom of the oxygen atom to one of the others. The proton then gets picked up by attaching itself to a lone pair on the unreacted ethanol molecule and then dumped back onto the oxygens more or less at random. In step 4, the molecule of water is lost from the ion. After losing the water, a protonated ester is given. If you recall from the first step, the oxygen by the reaction with the hydrogen sulfate ion is very important because this oxygen removes the hydrogen that is needed to form the ester. In order for the formation of the ester to be favored, it must be shifted to the right in favor of the product by using excess of acidic acid. To upset the equilibrium, we can, by Le Chantier's principle, increase the concentration of either the alcohol or the acid. Acid is used in excess because it is less expensive than isopentyl alcohol and more easily removed from the reaction mixture. An infrared spectrum of the product revealed that it was an isopentyl acetate. A peak at about 1,743.55 centimeters indicated the presence of a carbonyl group. At 1,006 indicated a COC bond. The peak at about 2,960 was indicative of an alkane group, CH2 groups. Also, the peak at 1,387 indicated alkane bonds which include an isopropyl split. As can be seen in the structure of the product, isopentyl acetate contains an isopropyl group at one end. It also contains a carbonyl group, a COC bond, and an alkane CH2 groups. There is a small presence of an OH group still present, and this could be because there is still water present and more drying reagent was needed. Or not all the isopentyl alcohol was converted to isopentyl acetate because of impurities.